what we were going to do is we were going to take this rational expression and we're going to make it into a over x plus 4 plus b over x minus 2 plus cx plus d divided by x squared plus 3x plus 8. So what I'll start out for, you'll have a times the other two denominators, and then you'll have b times the other two denominators, and then cx plus d times these two. Okay, and then you multiply everything out, and you're going to group together the x to the fourth terms, x cubed terms, x terms. Actually, you can't have that many. There's only 4 constants. It must be to the x to the fourth as the highest order. So I'll be back in just a second. My cable's a little short here today. I couldn't find my longer cable. I'm not sure where it is. Anyway, so let's, what were we doing here? So actually, it's the x cubed is the biggest term. So the question is, how do you do these multiplications? Well, there's 2 ways you can do them. You could set them up like this and kind of do them like you do long division. So what you would do is you take this times each one of those. So you get negative 16 minus 6x minus 2x squared. And then the next row, you'd shift over 1, and then you'd have 8x plus 3x squared, and then x cubed. And then you would add the columns together, but you don't carry anything. So you'd have negative 16 plus 2x plus x squared plus x cubed. Okay, so that's the first one. So you take this times that, this times that, this times that, gives you that row. Then this times that times that times that gives you that row. You align the columns and then just add them together. So the next one would be x squared plus 3x plus 8 times x plus 4. So do the same thing there. And then the last one, what you'd have to do is you'd multiply this out. So you get x squared plus 4x minus 2x, so that'd be plus 2x minus 8 times cx plus d. So in that case, you would have x squared plus 2x minus 8 times cx plus d, and then you multiply that out. And so ultimately you'd end up with a times negative, or plus, sorry, I'll do the first one for you, you can do the rest of them. So you'd have a times x cubed plus x squared plus 2x minus 16. And then you'd have b times the next thing, and then you'd have whatever you get when you multiply that thing out. And then you combine, you'd group the x cubed terms together and the x squared terms together, and the coefficients associated with those terms, and put them all together, and you'll end up with 4 equations and 4 unknowns ultimately. Okay, so I'm going to let you work on that for a minute. is a little longer. This is working. Yeah, it is. So when you get to that point, you have four equations and four unknowns. You know how to solve them using your calculators or physics. The people who haven't done that, then I'll show you how to do it. But some of you here, you may know how to do it. But I think, well, at least it doesn't take long to change. If we make a mistake somewhere along in this process, make sure we're on the same page. Did anybody go to the play this weekend? Was it any good? Yeah. It was good? Good. Did Xavier make it through without getting injured? Or he was talking about, getting slammed into the table?
One night he landed really weird and like hit his tailbone,
Yeah.
but he was fine.
Was he?
Yeah.
Okay.
He scared us every time though.
Yeah.
There was in the backstage like.
Oh, you were one of the stage crew?
No, I was in it, but.
Oh, you were in it.
Backstage.
Oh, okay. Okay, I didn't know you were in it. So remember, you have to go back to the original and get the coefficients here, 1, 3, 4, and 7. Anybody confirm I did that right or wrong?
It's exactly what I got.
You got exactly what you got? Okay. So let's kind of look what we did here. So this one should have been easy. Here, I ended up not adding them together because they don't combine. So I just ended up looking. So let me just move this page out of the way for a second. So when I took this one, so what I did is I took A times the product of these two, which was this part. So this times that, which was this times that, is that. So you get A times the whole thing. A times x cubed plus x squared plus 2x minus 16. Then you get B times the product of these two, which was this result. So you get x cubed plus 7x squared plus 20x plus 32. And then back over here, all I did was I started here, cx cubed plus 2cx squared minus 8cx plus dx squared plus 2dx, which I forgot the x initially, but I knew I made a mistake because I only had one x term and I knew I needed two of them. And then you have minus 8d. So once you've got all those written out, then I ended up just looking at the different terms. So looking back at my original expression, I had 1, 3, 4, and 7 for the four coefficients. So that I wrote those down. 1x cubed plus 3x squared plus 4x plus 7. And that has to be equal to the terms that involve x cubed for 1. So I've got a here, I've got b there, and I've got c there. So those are the three terms that involve x cubed. And then I've got x squared here, I've got x squared there, x squared there, and x squared there. So I'll have a plus 7b minus 8c, well, plus 2c plus d. So that's how I got that. And then I did the x terms. So I've got a times 2, so I get 2a, and b times 20, so I got 20b. And I had negative 8c plus 2d. And then finally the constants, I've got a times negative 16, so I've got negative 16a, b times 32 plus 32b. There are no terms that involve c that have just a constant, and then negative 8d. So that's my, those are my four equations. And so if you guys remember what we did in physics, is we would create this coefficient matrix which has the coefficients in front of a, b, c, and d. So I'm going to just write those up here, a, b, c, and d. And we do x cubed, x squared, x, and the constants. So for the x cubed, I've got 1 in front of all three of those. And I've got a 0 in front of d. So there's plus 0d. And then the second one, I have 1, 7, 2, and 1. 1, 7, 2, and 1. The third, I've got 2, 20, negative 8, 2. And the final, I've got negative 16, 32, 0, and negative 8. So that's my coefficient matrix. And we multiply that by the column vector A, B, C, D. And that equals the other side, which is 1, 3, 4, and 7. Okay. So all we have to do, if we call this matrix A, call this matrix X, and this matrix B, to solve for X, we just have to take the inverse of matrix A times B. And that'll give us the coefficients A, B, C, and D for the original expression. So some of you guys haven't had physics, so I'm going to show you how to do this on your calculator. To use this kind of calculator. Don't worry, I'm not going to do this on a exam or anything like that, but I just wanted to give you a challenging problem to work on. It's funny, this is a nice fancy one, but I like the one in the other room because this one always doesn't have very good lighting, so I don't know how you do this. It's got to be some better way. I couldn't have designed this bad. Okay. So we'll work on this. Okay. So remember what we do is you go to, let me show the keyboard here. So let me clear it. You go to second matrix. So you go to the matrix stuff. And we go to edit. And the matrix is 4 by 4. You can see here, 4 by 4. So all we have to do is we just pick matrix 1. And it's already the right size, 4 by 4. If it wasn't, we'd put 4. Well, let's go back up. So if it wasn't already 4 by 4, I'd go 4, enter, 4, enter, and then you just enter the coefficients from the matrix that we came up with, which was 1, 1, 1, 0, 1, 7, 2, 1, 2, 20, -8, 2, and -10, 32, 0, -8. Oops, sorry, pushed the wrong button there. So let's go back here. I'm sure it's got all the good stuff in there. Okay, so let's go back down to the last row. 0, what was my last? -8. I know what I did. -8. Okay. So that's the 4 by 4 matrix. And then what you do is you go back and do it again. So you go second matrix. B is already a 4 by 1, which is what we want. So that's good. And we go over to edit, pick 2, and it's 4 by 1. And then we just put the coefficients in 1, 3, 4, and 7. 1, 3, 4, 7. Okay. So those A and B matrices. And then all you have to do is go to the matrix, pick matrix A, do x to the -1 power, and then go to matrix and pick matrix B. So it says A inverse times B, and we get that, and then we push fractions so we can get into fractions. So you go to math, choose fractions, and so those are the answers: 25, 66, 10, 30 thirds, 7 20-seconds, and -3 20-seconds. Okay, so those are the coefficients that we come up with. Yeah.
I think on your matrix A, you might have to
Okay, let me just double check it. Yeah. Let's see here. How do I do this? Matrix A. Okay, 4 by 4. So it's 1, 1, 0. Second row is 1, 7. Is that 2? Yeah, 2, 1. 2, 20, -8, 2. Okay. I put -10 in. Okay, thank you. Said -16. 32, 0, and -8. Okay, I think I've got it right now. Okay, so we'll quit. Just do, and then we go to fraction. Fraction. So is it 25 over 72? Okay. So don't worry about it if you don't understand exactly how I did that. But what you end up with is the A coefficient is 25 over 72. The B coefficient is 35 over 108. The C coefficient is 71 over 216, and the D coefficient is -59 divided by 216. Okay, now we'll come back to that in a second. We're going to take a little break here. One of the sections that let me switch back to the laptop. So I wrote those down, but you didn't see them. There they are. So we skipped one section in Chapter 8, which is called Integration by Using Tables. So people really don't use that anymore because we have computers to do a lot of this stuff for us anyway. But I thought at least show you this. It's kind of like an artifact. It's from like ancient tombs in Egypt. But this was everybody who took math and engineering in the 70s, before the 70s, would buy one of these. CRC, Standard Math Tables, 24th edition. I don't know what year that would be. 1976. This was hot up the press when I bought it. And that was the first year that they required scientific calculators. So when you were using a slide rule, if you needed to get logarithms or sine, cosine tangents, you would have to use tables to get a reasonable value. So I'm just going to show you what these things look like. So I'll have to put that back. So let me go back to the document camera. This is actually as a document, so it might. This is terrible. I don't know why. Seems like I'll work better than that. So, for example, here is the trig functions for angles in radians. So you'd have, so x is radians. So there must be a previous page to here. Yeah, there we go. So that's the original part of the page. So if you had to look up the sine, cosine, cotangent, cosine. I guess you can get secant and cosecant by taking the reciprocal of it, but you can see the sine of 0 degrees is 0, the tangent of 0 degrees is 0. And so they would have that for radians. They also had trig tables here for using degrees, and they went to, so you would have degrees here. So this is 34 degrees. And then you would have fractions in terms of minutes. So 34 degrees, 60, you would break that up into 60 parts. So then you have 35 degrees. So it's fairly, and they go out to 5 decimal places as far as the sine, cosine. Oh, there is secant and cosecant. Okay. You had things like trig identities. So a lot of times, so all these different trig identities. You had exponentials, you had logarithms, all kinds of stuff. You had even more trig identities here that we don't have in our book. Yeah. But one thing they had was integration tables. So hopefully I can get this so you can see. So I mean, we've got an integration table that has about however many on our sheet of paper. What, maybe 25 or something like that, 30. And you can see some of them here. So for example, 11, the integral of e to the x dx is e to the x. The integral of the logarithm of x dx. Well, this is not one that's on our table, but we could solve for it using integration by parts. So it's x times the log of x minus x. So we could solve this one here is the arctangent. So some of them we've seen before. But if I look at my exact, my integration tables here have 728 integrals. So what you would do is, instead of you trying to solve these using whatever methods that we have been doing. So for example, let's just pick one out here. Here's x times the cosine of ax dx. How do you think we'd solve that? Do you remember? Probably integration by parts. This would be u, and this would be dv. Same with these things. These would be integration by parts. But they've done them for you, and you've got some constant a, so it's not just cosine of x, it's cosine of ax. And you can do that. You can look at some of these things that we've been solving using trigonometric substitutions. Let's see if I can find some of those. Those are probably up here near the front. Yeah, here we go. So it says forms containing x squared plus or minus a squared. So again, all of these we could solve using trig substitution. We would use, this would be u squared plus a squared. So we'd use the tangent trig substitution. If it's minus, apparently that just affects the minus sign in there, ultimately. And but a lot of these you can identify as hopefully how we would use trig substitution. These would be mostly using the arctangent or the arcsecant. We'd have plus x squared plus a squared, we'd use the tangent. And if we were using minus a squared, we'd use the secant. And then there's probably a whole bunch of ones where you have a squared minus x squared. Let's see if I can find those. There we would use, there we go. So now we've got another bunch of tables. So again, we could use, now this one's more difficult because that looks like it's cubed, I think. Or is it squared? Yeah, this one's cubed. So I'm not sure exactly. That looks almost like it's using that second type of u substitution in conjunction with trig substitution. Anyway, that's what section 6 deals with. It's using trig tables. And really what you're doing is you're just looking at the integral and saying which one of these formulas do I need to use. Okay, so now back to the problem of the day. So now that we have these coefficients, let's go back and look at what it results in. So this is what we're going to do. We're going to use those coefficients now. And that's not what I wanted to do. So what we'll have is we will have, if we do this as an integral, we'll have the integral, and we're going to factor out the a, so that always works out best. So we'll have 25 over 72 times the integral of 1 over x plus 4 dx plus b, which is 35 over 108 times the integral of 1 over x minus 2 dx. Now the third part, what we're going to do is we are going to factor out the denominator again. So we'll have negative 1 over 213 times the integral of, because 216. So we have 71x and actually we're going to put a plus sign there, minus 59, all divided by x squared plus 3x plus 8 dx. So the first two are easy. It's going to be just the natural log of the absolute value of x plus 4 and x minus 2. The third one's a little more difficult, so we're going to do that by ourselves here. So what we need to do is we need to rewrite this as two parts. And if we take the derivative with respect to x of the denominator of that expression, what we'll get is 2x plus 3. So remember what we do here is we set 71x minus 59 equal to a times 2x plus 3 plus some constant b. So we just need to figure out what a and b are. So you get 71x minus 59 is equal to 2ax plus 3a plus b. And just like we've done previously, we're going to break it up into the x parts. So you get 71 is equal to 2a, and negative 59 is equal to 3a plus b. So I've set the coefficients associated with the x terms equal to each other. So you get a is 71 over 2. And then you use that value of a to solve for b. So b is going to be equal to negative 59 minus 3 times 71 over 2. So that is what we get. So you get negative 118 over 2 minus 221 over 2, which is negative 341 over 2. I think that's right. 3, no, that's not right. 39. So you add these two together, you get 339 over 2. So that's the coefficients here. So what we can do is we can take this last expression, and we'll have 1 over 216 times the integral of a, which is 71 over 2, times 2x plus 3 divided by x squared plus 3x plus 8 dx.
Dr. Nicholson?
Did I make a mistake?
Well, I don't know. I got negative 331 over 2.
Oh, is that what? Oh, is this 18 or this is 8? So 118 plus 221. 118. Oops. 118 plus 221 is 339. It's just my handwriting, probably.
Yeah, it's supposed to be 213 instead of 221.
Oh, this? Oh, I just multiplied it wrong? Oh, you're right. Yeah, thank you. Yeah, you're right. That's what happens when you use your brain instead of your calculator. 71 times 3. 213. Yeah, you're right. Okay, so that's 231. Thanks for catching me before we went too far. Okay. So that's, let's see, 213 over 2. So you add those two together. So use my calculator. It's Monday morning. 331. Okay. So, good. So now we don't. And then, so what we're doing is we're replacing this with these two terms. And then you're going to have the next part, which is, you got a negative sign somewhere here, right? Negative, yeah. Except we already have it here, so we don't have to worry about it. We're not going to do it twice. So you'll have 1 over 216 times the integral of, there's a negative sign there, 331 over 2 divided by x squared plus 3x plus 8 dx. Is that right? I think so. So this one, we will end up with the natural log of the absolute value of x squared plus 3x plus 8 times this stuff. And here what we have to do again is we now have to rewrite this expression in the denominator's perfect square, which is not quite as simple. So I've made this really difficult. So you take 3 divided by 2, which is 3 halves, you square that, you get 9 fourths. So you add 9 fourths, and you subtract 9 fourths. So the denominator in this part can become x plus 3 halves squared, and then we have 32 minus 9, which is 23. 32 minus 9, which is 23. So we end up with plus 23 over 4. So 8 minus 9 fourths is 23 fourths. 32 fourths minus 9 fourths. Okay, so this denominator becomes that. So this, in the second case, u will be equal to x plus 3 halves, and a will be equal to the square root of 23 over 4, or the square root of 23 over 2. Square root of 23 fourths over, square root of 23 fourths is the square root of 23 over 2. So we'll get that factor when we do the arctangent and everything. Okay, so let's put this all together. So whoops, you just need a page right there. So the final answer is 25 over 72 times the natural log of the absolute value of x plus 4 plus 35 over 108 times the natural log of the absolute value of x minus 2. And then we have plus 71 over 432 times the natural log of the absolute value of x squared plus 3x plus 8. And then the final one will be negative 331 over 432 times 1 divided by, okay, I'm going to have to go to the next page now because I had my stuff over here. 1 over the square root of 23 over 2 times the arc tangent of x plus 3/2 divided by the square root of 23 over 2 plus c. Okay, so it's not that much different than the last problem. We had the same bunch of terms. With the linear terms, which is the only ones you're going to have to worry about. Like I said, this is way beyond anything I put on a test, but it kind of shows you the different, one of the things I said at the beginning of calculus was that calculus problems can get very long. Okay? So this is kind of the ultimate how long can the problems get. And it's all stuff that we learned in all these years, but it's accumulated and finally put all together into a nice package. Now, I could get rid of the square root of 23 in the denominator, but I'm not going to worry about that right now. I've gotten to the end of the problem, and so I'm happy with that. I haven't made any more mistakes. Okay, anybody got any questions about that? Ultimately, this all comes down to finding the area underneath the curve. And the reality of the situation is this is much more difficult than you'd ever need if you were being an engineer. If you got to a problem this complicated, you probably just do it numerically and plug it in the computer. But it just allows us to get practice at a lot of the skills that hopefully we know what we're doing. Okay, so that's it for partial fractions. I already assigned the homework, so. And we're skipping section 6. So now we're going to start section 7, which is kind of stepping back a little bit. It's kind of interesting. Did you see it might snow Tuesday night? 3 to 5 inches? What's that? You like that? I haven't seen that yet. So you can turn that thing in at the end of the period. Yeah, let's see what it says. Weather forecast. Today, it was 1 to 3 inches the other day, but now they're saying 3 to 5 inches. Let's see. Tuesday night, snow accumulating 3 to 5 inches. And then during the day, less than 1 inch. Let's go to Saturday, see if it says anything. Oh, yeah, it says about 1 inch. It's not anything significant. We keep thinking this is the last snow day, right? And it happens again. Okay, so section 7 is actually needed to do section 8. So section 8 is integration. Section 7 is actually derivative. And there's only a small part of section 8 that you need to know this for. And what this is it's for finding the derivatives of expressions that are indeterminate. So if you take the derivative of an expression and the result is actually that's not true. If you have an expression, a function whose slope is indeterminate, and you can't you can't use any of the previous techniques, canceling out or dividing out, rationalization, or the squeeze theorem. Then you can use L'Hopital's rule for indeterminate derivatives. Indeterminate, not derivatives, but you'll see here in a second. So previously, meaning all the way back to chapter 2, when we talked about taking limits, so this is actually to do with limits, there were cases where if we plugged in the value of x into the expression, we got 0 divided by 0, and that's where we used dividing out, rationalization, or the squeeze theorem. In this case, I could use dividing out by factoring the numerator. So let's just do that. So this is how we did the, back in chapter 2. We said, okay, if we plug 4 into our equation, so you get that, and you'll get 0 divided by 0. So now what do? You can't just say we quit. It's not 0, it's not infinity, it's indeterminate. So the way that we handle that is we factor the numerator, which is going to be x minus 4 times x plus 1 divided by x minus 4, and the x minus 4's cancel out, and so the limit of the original expression is the same as the simplified expression. So at this point, the function is not indeterminate, the result is not indeterminate, so you just plug the number in, so you get 4 plus 1, which is 5. So that's the answer. So that's how we used to do it. Now, L'Hopital's rule says this. It says if you're trying to find the limit of a rational expression where you have f of x in the numerator and g of x in the denominator, then the limit of that ratio is also equal to the ratio of the limit of the derivatives. And what taking the derivative does for you is also removes the indeterminacy. So in our case here, our simple case, which we already know what the answer is, which is 5, f of x is x squared minus 3x minus 4, and g of x is equal to x minus 4. So if we take the derivatives of those, we get 2x minus 3, and we get g prime of x equals 1. So we don't put the dx on because it's not du. This is actually the derivative. So what we can say is that the limit in this case is x approaches, 4. And it really doesn't have to be 4. It could be any number. It'll still work out. But in this case, at x equals 4, it's indeterminate. So it's this. We could have, if it was anything other than x equals 4, we just plug the number and we'd be done. But when we plug x equals 4, we get indeterminacy. So that's the same as the limit as x approaches 4 of 2x minus 3 divided by 1. And at this point, you can see if I plug the numbers in, it is not indeterminate. And so I can just evaluate, and you get 5. 8 minus 3 is 5. So there you go. Got the same answer. One using the dividing out technique, this using L'Hopital's rule. It's L'Hopital, not L'Hopital or whatever.
That's what I thought.
That's what. Yeah, speaking of languages, I'm going to show you something. I've got to hook up the speaker. Okay. So it turns out, the indeterminate form that we've been dealing with has been 0 over 0, but there are other indeterminate forms. So infinity divided by infinity is also indeterminate. Infinity minus infinity is indeterminate. 0 to the 0th power, 0 to the 0 times infinity, 1 to the infinite power. So those are all other indeterminate forms which can be used. You can use L'Hopital's rule in case you end up with those kinds of situations. Most of the time it is 0 over 0, but it doesn't have to be. For example, if you have, well, let me just find one, and we're not going to solve it, but I'm going to show you like this one. So if you took the limit as x goes to infinity of x cubed over e to the x divided by 2, you would say I'd have infinity over infinity if I plugged an infinity in there. So that is also an indeterminate form, which can also be addressed using L'Hopital's rule. Okay, so we'll do that tomorrow. I think we'll have school tomorrow. Maybe not Wednesday. So remember let me just turn this thing up for a second.